Good morning, everyone. This is an audio recording for visually impaired student. Today, I am going to read a chapter from Physical Chemistry. Chapter 3 Spectroscopy. Introduction. Spectroscopy is a branch of science which deals with the study of interaction of electromagnetic radiation with matter. The most important feature of electromagnetic radiation is that energy is absorbed or emitted by the matter in discrete amount called quanta. Spectroscopy techniques are generally used to measure the energy difference between various molecular energy level and to determine the atomic and molecular structures. The instruments used in such studies are called spectrometer. Special devices are added in spectrometers for the automatic recording of spectra. The spectrum of the molecule is presented as a continuous graph by plotting either absorbance or transmittance of electromagnetic radiation as the function of wavelength or wave number over a particular range. Characteristics of electromagnetic radiation. The term electromagnetic radiation represents the radiant energy emitted from any source in the form of heat or light. These waves have both electric and magnetic field associated with them and are therefore known as a electromagnetic radiation. Some important characteristics of the wave are given below. First, these waves are associated with both electric and magnetic field oscillating perpendicular to each other and also perpendicular to the direction of propagation of the wave as shown in figure 1. Second, they have dual nature, particle nature as well as the wave nature. For example, a beam of light is a stream of particle called photons moving through space in a form of wave. Second, they do not require any medium for propagation. Third, they travel with the velocity of the light c is equal to 3 into 10 to the power 8 meter per second. All these waves are characterized by their wavelength lambda, frequency mu and velocity c according to the equation mu is equal to c upon lambda or lambda is equal to c upon mu. So c is equal to mu into lambda. The quantity 1 upon lambda is equal to mu bar is known as a wave number. Reason of electromagnetic spectrum. When the different type of electromagnetic radiations are arranged in order of their increasing wavelength or decreasing frequency, the complete arrangement is known as a electromagnetic spectrum. This is shown in table 1. The increasing order of wavelength of electromagnetic radiation is cosmic ray, then gamma ray, then X-ray, then UV ray, visible ray, IR rays, microwaves and radio waves. Reverse is the order of electromagnetic addition in increasing order of energy as given below. Any wavelength of light that a particular molecule will absorb will be due to change in the electronic, vibrational and rotational energy level permissible for its atom, since each mode of excitation require a specific quantity of energy, so the different absorbance occur in a different region of the electromagnetic spectrum. Thus, the interaction of radiation with matter in different ways by various processes gives rise to different branches of spectroscopy as shown in table 2. Gamma rays show the electronic spectra, UV and visible show the rotational and vibrational spectra, microwave show NMR and NQR. Basic feature of spectroscopy. Introduction to molecular spectroscopy. When energy is absorbed by the atom, their electron jump to higher energy level and while coming back to their ground state energy level, they emitted the energy equal to the difference between the energy of two levels. This emission of radiation by an atom is known as atomic spectra. For example, atomic spectra of the hydrogen atom containing a number of lines like the Lyman series, Balmer series, Pascal series, Brackett series, and Pfund series. However, in the case of molecule, when the energy is absorbed, it can undergo rotational, vibrational, or electronic transition depending on the amount of energy absorbed. Just as electronic energy is quantized. There are only discrete electronic energy level in an atom or a molecule. The rotational and vibrational energies are also quantized. That is, There are only discrete rotational and vibrational energy level in the molecule. These rotational, vibrational and electronic energy level of the molecule are collectively known as molecular energy levels. The transition of energy can take place only between these levels and result in molecular spectrum. The molecular energy level are shown in figure 2. It is clear from the wave energy level diagram that each electronic energy level is associated with the series of vibrational energy level mu, and each vibrational energy level is associated with the series of rotational energy level j. The lower energy level are designed by mu and j, whereas the higher energy level are designed by single prime mu bar or j dash. When the energy absorbed by a molecule is so large, then an electron can jump from one electronic energy level to another. Then, as the energy required for transition from one vibrational level to the another is much less, and from one rotational to the another is still less. Thus, electronic transition is always accompanied by the transition between the vibrational levels as well as the rotational level. Thus, molecular spectra is much more complex than the atomic spectra. Atomic spectra contain lines, whereas the molecular spectra contain group of closely spaced lines. Each such groups is known as band. As atomic spectra help in the study of structure of atom, the study of molecular spectra give even more information about the structure and the property of molecule, such as bond length, bond angle, bond strength, shape, moment of inertia and the dipole moment, etc. Absorption and emission spectroscopy. As we know that molecular energy levels are quantized, the transition between these energy levels take place according to certain rules known as selection rules. To understand how does a spectrum rise, consider two molecular energy level E1 and E2 with energy difference delta is equal to E2 minus E1, which is equal to h mu as shown in figure 3a and b. The transition between any two energy levels can take place in either of the following two ways. First, the transition may take place from lower energy level to higher energy level by absorbing energy. This is known as absorption spectroscopy, and the spectrum thus obtained is known as the absorption spectrum. Second, the transition may take place from higher energy level to lower energy level and thus emitting the excess energy as a photon. This is known as emission spectroscopy, and the spectra thus obtained is known as emission spectrum. In above cases, the energy of the photon h mu emitted or absorbed is given by delta is equal to E2 minus E1 is equal to h mu is equal to hc upon lambda. As in term of wavelength, lambda is equal to hc upon delta, or in the term of wave number, v bar is equal to v upon c. If it may be noted that both emission and absorption spectroscopy give the same information about the energy level separation. Generally, the absorption spectroscopy is used as it is easier to interpret than emission spectra. Emission spectroscopy is used only when the visible or UV light are used. Experimentally set up for the absorption spectroscopy. The diagram of spectrometer used in absorption spectroscopy is shown in figure 4. It consists of mainly six parts. Name first source of radiation. The source of radiation in the spectrometer is a tungsten filament emitted visible light for the visible region or hydrogen discharge lamp if the spectra in UV region are to be taken. Second, slit. The slit is used to get a fine beam of radiation coming from the source. Third, monochromator. The monochromator is a device used for getting the monochromatic radiation, that is, the radiation of single frequency. Fourth, sample cell. The sample cell contains the compound for which the spectrum is required. The monochromatic radiation falls on the sample cell. Fifth, dispersing element. To analyze the spectral radiation, the dispersing element is used, which is generally a glass prism or a quartz prism or a diffraction grating. Sixth, detector. Detector is a device which converts the spectral radiation into an electrical signal that is transit to a recording device called a recorder. The recorder produces either a print on the chart or giving a computer record of the spectra. Signal to noise ratio. To magnify the detected signals, the electronic amplification devices is used in the spectrometer. Then these magnified signals are passed on to a recording device to produce a plot on a chart. One such plot is shown in figure 5th. It is clear from above figure that there are number of the random peaks in the background of spectrum. These random peaks are known as a fluctuations. These fluctuations are known as a noise, denoted by capital N. These fluctuations are due to some component presented along with the sample or maybe due to their false electronic signal produced by the detector. In order to distinguish the real spectral peak as from the noise, the intensity of real peak should be 3 to 4 times more than that of He noise signal. There are different ways to improve the signal to noise ratio S upon N or SNR. First, the use of hardware devices such as filter, lock-in amplifier, etc. can enhance SNR. Second, by damping out the oscillation of the recorder pan, the SNR can be enhanced. This will make pan less susceptible to high frequency noise and the baseline of the spectrum will be smoother. Third, the spectrum of the solvent or background can be stored in computer and subtracted from the observed spectrum in order to isolate the spectrum of the substance. For example, in IR spectrum, the signal due to CO2 are subtracted. Fourth, still another technique involves the recording of the spectrum into steps and store the intensity of point in a computer memory. In one scan, a big signal may not be visible above the noise level, but after n scans, the signal will be n time larger in the store. But n scans increase the noise only by n upon 2, so there is a net increase in s upon n ratio. Fifth, the software technique like Fourier transformation has gained a lot of importance in spectroscopy. This technique involves mathematical operations and described below. A. The general method of representing the spectra in the form of intensity of radiation as a function of frequency. Second, another method of representing the spectra is in the form of intensity of radiation as a function of time. Thus, there are the two types of spectrum. One is a frequency domain and other is a time domain. Contain all the information about the spectrum that contains and vice versa. I into mu can be transformed into F into T by a mathematical operations known as Fourier transformation. Similarly, F into T can be converted into I into mu by inverse Fourier transformation. The advantage of FT spectroscopy is its speed. With a very small computer, it is possible to carry out the FT of the spectrum in a few seconds. To observe the spectra in the frequency domain, a good ideal of time is required because scanning has to be done gradually over a long range of frequency. But to observe the spectra in the time domain, all frequency can be applied at once to the sample within a very short interval of time. Thus, time domain spectrum is very fast as compared to frequency domain spectrum, which may require 15 minutes to scan the spectrum. This rapid scanning enhances the S upon N ratio. Fourier transformation technique is used in IR and NMR technique spectroscopy. Thus, we have FTIR, FDNMR, FTUV, etc. Spectroscopies. These techniques produces well-resolved absorption spectrum with a good signal to noise SNR ratio. Resolving power. The resolving power is defined as measure of the performance of the spectrometer. It is the ability of the spectrometer to distinguish adjusting absorption band or two very close spectral lines as a separate identities. No molecular absorption take place at a single frequency only, but spread over a range of frequency, usually very narrow but sometimes quite large. Let us consider two such lines close together as on the right of figure 6. The dotted curve represents the absorption due to each line separately. The full line represents their combined absorption. In procedure, the absorption peak passes through the exit slit and get registered on the detector. Figure 6a show unresolved absorption peak which passes through wide slit as shown in figure 6b and figure 6c, and finally detected a single peak, figure 6d. In this cases, the width of the slit is equal to the separation between the peaks, but if the slit is made narrow, the resolving power can be increased. However, if the slit is made too narrow, it always less energy from the beam to reach the detector and thus a weak signal will be observed. Thus an optimum condition is achieved where there is a balance between the slit width and the intensity of the absorption peak. By the use of very narrow slit, the detector register not only the main peak but give a diffraction pattern of the number of the smaller peak at plus minus lambda plus minus 2 lambda etc. from the center of the main peak as shown in figure 7. Type of molecular energies and Born-Opnier approximation. A molecule possesses four different type of energies. These are as follow. First, transitional energy. It is due to transitional motion of the molecule and due to the center of gravity of the molecular changes. Second, rotational energy. It is due to the rotation of molecule about an axis perpendicular to the internuclear axis and passing through the center of gravity of the molecule. Third, vibrational frequency energy. It is due to and fro motion of the nuclei of the molecule without any change in the position of the center of gravity of the molecule. Fourth, electronic energy. It is due to various electronic interaction in the molecule. By the absorption of energy, the transition of electron take place from the lower electronic energy level to higher electronic energy level. According to Bohr Oppenheimer approximation, the total energy of the molecule is the sum of transitional, rotational, vibrational, and electronic energy, i.e., E is equal to ETR plus E rotating plus E vibrational plus E electronic. Further, E electronic is greater than E vibrational greater than E rotational greater than ETR. Since transitional energy is negligible small, the Bohr Oppenheimer approximation can be written as E is equal to ER plus EV plus EE. Type of molecular spectrum. The molecular spectra arises due to the transitional or excitation between various energy level of a molecule. We already know the separation between the two electronic energy level is very large as compared to the vibrational energy level, which in turn have larger separation than the rotational energy level. The different type of molecular spectra observed depending upon the energy observed and the region of the electromagnetic spectrum in which they are observed, and these are explained as below. First, rotational or microwave spectra. If the energy absorbed by the molecule is low and such that the transition take place from one rotational level to the another rotation level, the spectra obtained is called the rotational spectra. These spectra is obtained in microwave region or far infrared region. V bar is equal to 1 to 100 centimeter inverse. That's why also known as microwave spectra. This spectra is known by the molecule having permanent dipole moment, for example H2O, ammonia, NO, HCl, etc. Second, vibrational rotational infrared spectra. If the energy absorbed by the molecule is large and such the transition take place from one vibration level to another vibration level within the same electronic level, then the energy required for the transition between the rotational energy level are still less. Both type of transition will take place. Thus, the spectra obtained is known as vibrational rotational spectra. These spectra is obtained in the near infrared region. V bar is equal to 500 to 4000 centimeter inverse. That's why also known as infrared spectra. This spectra is shown when a vibrational motion of a molecule is accompanied by the change in dipole moment of the molecule. Example CO2, water, ammonia, etc. Third, electronic spectra. if the energy absorbed by the molecule is so high that the transition take place from one electronic energy level to another, then these will also be accompanied by vibrational levels changes, and each of these is further accompanied by rotational level changes. For each vibrational changes, a set of closely spaced line is observed due to the rotational level changes. Such a group of closely spaced rotational lines is known as a band. Thus, for a given electronic spectra, a set of band is observed. This set of band is known as a band group or a band system. Thus, whereas atoms give line spectra, molecule give band spectra. As high excitation energy is required for electronic transition, the energy is available in the visible 12,500 to 25,000 centimeter inverse, and the ultraviolet region 25,000 to 70,000 centimeter inverse. Fourth Raman spectra. This is also a type of vibrational rotational spectrum and is based on the scattering of radiation and not on the absorption of radiation by the sample. A beam of monochromatic radiation of the visible region is made to fall on the sample, and scattering is observed at right angle to the direction of the incident beam. The scattering beam having frequency equal to that of the incident beam is known as a ray scattering, whereas the scattered light having different frequency than the incident beam is known as a Raman scattering. This spectra is observed in the visible region. Fifth, nuclear magnetic resonance spectra, NMR spectra. This spectrum rises from the transition between the nuclear spin energy level of the molecule when an external magnetic field is applied on it. The energy involved in this transition are very high, which lie in the radio region 5 to 100 MHz. Sixth, electron spin resonance ESR spectra. This spectrum arises from the transition between the electron spin energy level of the molecule when an external magnetic field is applied on it. These involve frequency corresponding to the microwave region 2000 to 9600 MHz. Selection rule in spectroscopy. Atomic as well as molecular spectra are obtained due to the transition between different energy levels. However, such transition can take place only between definite energy level and not between any two energy levels. The restriction thus applied on the transition as governed by the certain rule is known as a selection rule. If these rules are followed, the transition can take place and is known as a allowed transition. If these rules are not followed, the transition cannot be take place and known as a forbidden transition. The selection rule depending upon the type of transition for a molecule to interact with the electromagnetic radiation and to absorb or emit a photon of frequency mu. It must possesses a dipole at that frequency, the dipole moment of which is known as a transition dipole moment. The intensity of the radiation is proportional to the square of the transition dipole moment. Thus, a transition is allowed only if mu t are not equal to 0. And hence, pure rotational spectra are observed only for the molecule which have permanent dipole moment. A gross selection rule specifies the general feature that a molecule must have in order to give a particular type of spectrum. The specific selection rules are generally expressed in the term of changes in quantum number for the allowed transition. For the pure rotational transition, the selection rule is del j is equal to plus minus 1, where j represents rotational quantum number. Similarly, for pure vibrational transition, the selection rule is del v is equal to plus minus v, where v represent the vibrational quantum number. Width and intensities of the spectral line. Two very important property of any spectral line are: first, width of the spectral line, how sharp or broad is the peak; second, intensity of the spectral line indicate how strong or weak is the given peak. First, the width of the spectral line. A sharp spectral line having no width is shown in figure 8a. Actual we observe line having certain width as shown in figure 8b. Factor contribute to width of the spectral line. The factor which causes broadening of the spectral line are colos broadening, Doppler broadening, and lifetime broadening. Collision broadening. In the gaseous or liquid phases, the atom or a molecule continuously collide with each other. This collision causes distortion of the electron cloud of outer electrons and hence the energy level of these electrons are also disturbed. The transition between perturbed level causes broadening of spectral line. The collision broadening account for the width of visible and ultraviolet spectral line. With Doppler broadening. The cause of this broadening is Doppler effect. According to this effect, the frequency absorbed or emitting radiation changes when the molecule is moving toward or away from the observer or the observing instrument. Collision broadening is most important factor for liquid, but for gaseous, Doppler effect account for the width of the spectral lines. According to the kinetic theory of gases, the molecule of the gases are continuously moving in a random motion. If a molecule is moving toward the observer with velocity mu, then the velocity v dash of the radiation seen by a molecule is v dash is equal to v into 1 plus mu upon c, where mu is the actual frequency of radiation. When the molecule is moving away from the observer, the frequency of radiation seen by the observer is V dash is equal to V into 1 minus mu upon C. On rearranging equation first, we have V minus V dash upon V is equal to minus mu upon C. Rearranging equation second, we have V minus V bar upon V is equal to mu upon C. The quantity V minus V dash is equal to del V is called the Doppler shift or the Doppler broadening. In the gaseous sample, molecules are moving in all possible directions with the different speeds. Some are moving toward the observer and some are moving away from the observer. Thus, the observed frequency becomes higher or lower than the actual frequency of the radiation. All resulting Doppler shift causes broadening of the spectral line. Figure 9 showed Doppler broadening spectral line at three different temperatures. From the kinetic theory of gases, it is known that Doppler broadening of a spectral line of a molecule of mass m at a temperature T is given. Del mu is equal to 2 V upon C under root 2 kT ln 2 upon m. Thus, we can say that Doppler broadening increases with increase in temperature because the molecular speed increases with increase of temperature. And hence, it is the best to work at low temperature to obtain the spectra of maximum sharpness. See lifetime broadening. These type of broadening occur in all type of sample, gaseous, liquid, solid or solution. This is based on the fundamental uncertainty principle. According to this principle, energy level of a molecule are not sharp but are blurred or the energy of the levels can changing with time. The Hinsberg uncertainty principle says that if a system exists in an energy state for a time of del t seconds, then the energy of that state will be uncertain by amount del E. Mathematically, del E into del t is equal to h upon 2 pi. Here, del t is called the lifetime and del E is the energy uncertainty of the state of corresponding uncertainty in the radiation frequency in the term of wave number is del V bar is equal to 1 upon 2 pi del T. The quantity del E or del V bar is called the lifetime broadening or uncertainty broadening. It is clear from equation 4 that del V bar is inversely proportional to del T. Thus, shorter is the lifetime of state involved in transition, larger is the broadening of the spectral line. The actual broadening of spectral line are far more dependent on collision and the Doppler broadening on the lifetime broadening. Second, the intensity of spectral line. The intensity of spectral line depend on three main factors. A. Transition probability. The probability of transition occurring from one energy level to other. B. The population or the number of molecules initially present in the state from which the transition take place. C. Intensity of the incident radiation. The transition probability means whether a particular transition will occur between two given energy level or not. The selection rules determine whether a particular transition is allowed or forbidden. The allowed transition give intense spectral line, whereas the forbidden transition either give no spectral line or a weak line. Similarly, when the intensity of incident radiations increases, the rate of transitions is increases, thus the intensity of spectral line also increases. The intensity of spectral line is proportional to the population difference between the two energy levels. At a given temperature, if N naught is the number of molecule in the ground state, then the number of molecule N in the excited state is given by the Boltzmann distribution law as N is equal to N naught E minus del E upon KT. On rearranging, N upon N naught is equal to E minus del E upon KT, where K is a Boltzmann constant, del is equal to E minus E naught. E is the energy of higher or excited state. E naught is the energy of ground state. If the value of del is large, then N upon N naught will be small. It means the excited state is less populated than ground state, and hence the spectral line arises from the transition between the ground state and the higher state will be more intense than those of arising from the transition between the first excited state to the higher excited state. Degree of freedom of motion. Consider a molecule made up of an atom. As all the mass of atom is concentrated in its small nucleus, and we know that size of nucleus is very small. The atom may be considered as mass point. To represent each mass point, we require three coordinates. Thus, to represent position of n masses point in the space, we require 3n coordinate. The number of coordinates required to specify the position of all the masses point. Example, atom in a molecule is called the degree of freedom. Thus, a molecule made up of an atom has 3n degree of freedom. According to kinetic theory of matter, when the thermal energy is absorbed by a molecule, it is stored within the molecule in the form of transitional motion of molecule and rotational vibrational motion of the atom within the molecule. The transitional motion of the molecule means the motion of the center of frequency of mass of the molecule as a whole. The center of mass of a molecule can be represented by the three coordinate, and hence there are three transitional degree of freedom. The remaining 3 and minus 3 coordinate represent the internal degree of freedom. The internal degree of freedom may be subdivided into first rotational degree of freedom, second vibrational degree of freedom. For a rotational motion, there are two degree of freedom. For a linear molecule and three for a nonlinear molecule as shown in figure 10a and 10b. The remaining degree of freedom describe the motion of a nuclei with respect to one another and thus represented the vibrational degree of freedom. Thus, vibrational degree of freedom of a linear molecule containing an atom is equal to 3n minus 5, and the vibrational degree of freedom of non-linear molecule containing an atom is equal to 3n minus 6. Let's consider some example for the calculation of vibrational degree of freedom. First, CO. It is a diatomic molecule and it is also linear. Its vibrational degree of freedom is equal to 3n minus 5, that is 1. Second, the CO2 linear polyatomic molecule. Vibrational degree of freedom is equal to 3n minus 5, that is 4. Third, H2O non-linear polyatomic molecule. Vibrational degree of freedom is 3n minus 6, that is 3. In this way, we can calculate the vibrational degree of freedom for both linear as well as non-linear molecule. In terms of coordinates, the vibrational degree of freedom represents the interatomic distance and angle to specify the geometry of the atomic framework within the molecule. In terms of molecular motion, the vibrational degree of freedom represents the number of independent vibrational modes that can occur in a molecule, the vibrational energy being associated with each mode. The only one mode of vibration for a diatomic molecule like CO, four mode of vibration of the linear triatomic CO2 molecule, and three mode of vibration of the non-linear triatomic H2O molecule as shown in figure 11. Energy level of a rigid rotator. The rotational spectra rises due to the transition between the rotational energy level of the gaseous molecule on absorption of light in microwave region. Example 1 to 100 centimeter inverse. This spectra is shown by a molecule having permanent dipole moment. Example water, ammonia, etc. The molecule having no permanent dipole moment do not exhibit spectra in the microwave region. The homonuclear diatomic molecules such as H2, O2, N2 are nonpolar and do not exhibit rotational spectra. Similarly, the symmetrical molecule CO2, HCH2, CH2, S double bond, C double bond S do not have permanent dipole moment and thus do not exhibit rotational spectra. A. Energy level of rigid rotator. On the basis of wave mechanics, it can be seen that if a diatomic molecule is considered to be rigid rotator, like a rigid dumbbell joint along its line of center by a bond length equal in length of the distance r naught between the two nuclei as shown in figure 12, then the allowed rotational energy of a molecule around the axis passing through the center of gravity and perpendicular to the line joining the nuclei was given. Er is equal to h square upon 8 pi square I into j plus 1, where j is a rotational quantum number having values 0, 1, 2, 3, etc. and I is the moment of inertia of the molecule about the axis of rotation. I is equal to mu r naught square, where m1 m2 are the atomic masses of the two atom of the diatomic molecule and mu is the reduced mass. Mu is equal to m1 into m2 upon m1 plus m2. Derivation of expression for rotational energy, center of gravity of a diatomic molecule in the point which satisfy the following condition: m1 r1 is equal to m2 r2. The moment of inertia of a diatomic molecule is given. I is equal to m2 r2 r1 plus m1 r1 r2. But R1 plus R2 is equal to R0, so R2 is equal to R0 minus R1. Put the value of R2. M1 R1 is equal to M2 into R0 minus R1. So finally R1 is equal to M2 R0 plus M1 plus M2. And similarly R2 is equal to M1 R0 upon M1 plus M2. Substitution this value in equation 5th we get I is equal to m1 m2 square r naught square upon m1 plus m2 का square plus m2 m1 square plus r naught square upon m1 plus m2 whole square, that is equal to m1 m2 upon m1 plus m2 into r naught square, that is mu r naught square. Now by the definition, the angular momentum of the rotating molecule is given. L is equal to I omega, where omega is the angular velocity. But we know that angular momentum is quantized, whose values is given. L is equal to under root j into j plus 1 into h upon 2 pi, where j is equal to 0, 1, 2, 3, called the rotational quantum number. Further, the energy of rotating molecule is given by Er is equal to 1 upon 2 I omega square. The quantized value of the rotational energy level will be given. Er is equal to L square by 2I. Substituting the value of L from the equation 13, we get Er is equal to h square upon 8 pi I into j plus 1. By putting j is equal to 0, 1, 2, 3, etc. in equation 15, the pattern of the rotational energy level updating will be shown in figure 13. Evidently, the spacing between the energy level increases as the value of J increases. Selection rule for rotational spectra. According to the selection rule, the transition takes place between those rotational energy level for which del J is equal to plus minus 1. The change in rotational quantum number is unity. The transition del J is equal to plus 1 corresponding to absorption and minus 1 corresponding to emission. In other words, a transition can take place from a particular rotation level to the next higher or just the lower rotation level. All these transitions can take place with equal probability, whereas all the transitions are forbidden. Rotational spectra of diatomic molecule. As discussed earlier, the allowed rotational energies are given by equation Er is equal to h square upon 8 pi square I into j plus 1. As E is equal to h mu, therefore in term of frequency we can write mu is equal to h upon 8 pi square I into j plus 1. Further, as C is equal to mu lambda is equal to mu upon V bar. Therefore, in the term of wave number, V bar is equal to Bj into j plus 1, where B is equal to h upon 8 pi square IC is called the rotational constant. Putting j is equal to 0, 1, 2, 3, the wave number of the different rotating level will be 0, 2b, 6b, 12b, 20b, 30b, and so on. When a transition takes place from a lower rotation level with a rotational quantum number j to the higher rotation level with rotational quantum number j, the energy absorbed will be given by del ER is equal to h square upon 8 pi square I into j dash plus 1 minus j into j plus 1. However, according to the rotational selection rule, only those rotational transitions are allowed for which del j is equal to plus minus 1, and hence in the present j dash is equal to j plus 1. Substituting this value, del er is equal to h square upon 8 pi square I into 2 into j plus 1. To express in a term of wave number, we put del E is equal to h mu, that is equal to h upon lambda, and that is equal to h into mu bar. So finally mu bar is equal to 2b into j plus 1, where b is equal to h upon 8 pi square ic is a rotational constant. V bar in equation 6 represent the wave number of the spectral line will be obtained as a result of transition between the rotational levels, putting j is equal to 1, 2, 3, etc. Transition j is equal to 0 to j dash is equal to 1, j is equal to 1 to j dash is equal to 2. On a general form j to j plus 1 involving the absorption of energy, the wave number of the line obtained will be 2b, 4b, 6b, 8b, and so on. The important feature of the pure rotational spectra is that every two successive lines have a constant difference of wave number equal to 2b. This is called the frequency separation or a wave number separation. Thus, the various lines in a rotational spectra will be equally spaced. The separation between any two successive lines will have difference in wave number given by del v bar is equal to h upon 8 pi square IC. Another important feature of the spectra is that intensity of different transitions are not equal. The intensity increases with increasing J, passing through a maximum and then decreases as J further increased. The main feature of rotational spectra are shown in figure 14. Relative intensity of rotational spectral lines. The relative intensity of the spectral line will depend upon the relative population of the energy levels. Greater is the population of an energy level, greater will be the number of molecules that can be promoted to the next higher level, and hence greater is the intensity of absorption. According to Boltzmann distribution law, the population of a rotational energy level with quantum number j is given by the equation nj upon n naught is equal to e की power minus ej upon kt. Rotational energy level are degenerate, and the degeneracy of an rotation level with quantum number j is given by Gj is equal to 2j plus 1. Thus, the relative population of an energy level, and hence the intensity of rotation line will be proportional to both of the above factor. Intensity is inversely proportional to nj upon n naught is equal to 2j plus 1 into e की power minus ej upon kt. Putting Eg is equal to Hc Bj into j plus 1. So we get Nj upon N naught is equal to 2j plus 1 e की power minus Hc Bj into j plus 1 upon kt. As the value of j increases, the factor 2j plus 1 increases, but the exponential factor decreases very slowly in the starting and rapidly as the value of j become higher and higher, and hence the graph of the rigid diatomic molecule between Nj upon N naught versus j is obtained as shown in figure 15. Type of molecules exhibiting rotational spectra. As mentioned earlier, the Gauss selection rule for obtaining a pure rotational spectra is that a molecule must have the permanent dipole moment so that it can interact with the electromagnetic spectrum and absorb or emit a proton. Thus, we can say that a pure rotational spectrum is obtaining only for a polar molecule, example water, ammonia, NO, NN2, etc. These molecules have permanent dipole moment, homonuclear diatomic molecule, and symmetrical linear molecule. Do not give rotational spectra as they do not have permanent dipole moment. Structural information from rotational spectra. By studying the rotational spectra, example by determining the frequency separation del V bar, it is possible to calculate the moment of inertia I by using the relation B is equal to J upon 8 pi square IC. Then by knowing the mass of atom present in the diatomic molecule, it is possible to calculate the distance between the atom R naught. For example, internuclear distance or bond length. Determination of bond length. The rotational spectra can be used to determine the bond distance of the atom as we know. B is equal to H upon 8 pi square IC. So I is equal to H की value 6.626 into 10 की power minus 34 upon 8 into 3.4 square multiplied 2.998 multiplied 10 की power 8 multiply B. So I is equal to 2.8 multiplied 10 की power minus 44 upon B J S square. As we know that I is equal to mu R square. So R is equal to under root I upon mu, and mu is a reduced mass. By putting the value of I and U in equation first, we can easily calculate the bond distance. Isotopic effect. When a particular atom in a molecule is replaced by its isotope, the resulting molecule is chemically identical with the original one. The internuclear distance does not change on isotopic substitution, but there is a change in total mass and hence change in moment of inertia I, and the value of B for which molecule is given as B is equal to H upon 8 pi square IC. As I appear in the denominator, the increase in the value of I decreases the value of B. In this way, the energy of various rotation level it decreases, and so the energy level in become close to one another, and hence the space between two adjacent energy level 2b is decreases. This can be explained with the help of an example. Consider CO molecule on moving from 12 CO to 13 CO. There is an increase in the mass of carbon atom 12C to 13C, and hence the value of B decreases. Therefore, the separation between the spectral line of 13CO will be smaller than that of the 12CO. The value of B and B dash can be written B upon B dash is equal to I dash upon I is equal to mu dash upon mu, where mu is the reduced mass and the internuclear distance remain unchanged on isotopic substitution. Thus B upon B dash is equal to mu dash upon mu. Using this equation, the atomic mass of 13C can be determined. The effect of isotopic substitution on the energy level and the spectrum is shown in figure 16. Isotopic effect can be used to determine the atomic mass of the isotope. The relative abundance of the isotope can be determined by comparison of the absorption intensities. Experimental details of microwave rotational spectroscopy. The source of radiation is a special type of electronic oscillator called klystron. It produces monochromatic radiation of frequency corresponding to wavelength ranges of 0.1 to few hundred centimeter. The energy corresponding to these wavelengths are same as required for rotational transition. The processor consists in passing the monochromatic energy of the microwave through the gaseous sample of the substance being studied and measure the intensity of the transmit radiation. By varying the frequency of the oscillator and observing the intensity of the transmit beam, the frequency at which absorption takes place can be determined from the plot of transmitted intensity versus frequency. From these data, the structural parameters like the moment of inertia, internuclear distance can be calculated. The experimental setup for the microwave spectrum is shown in figure 17.